This morning, I was Pierfrancesco is in the Department of Applied Mathematics.
Operations research. All right, nomenclature, you know.
And it would speak about an old puzzle in deep learning, which is implies implicit biases in SGD. So, Francesco.
Thank you. I think I have it. Okay, so thank you so much, Tommy, for inviting me here. On one hand, I feel very connected with this group of people because you also show up late to the first events in the morning. On the other hand, I think it's gonna be tough because, like, you know, when I give this talk in Princeton or in mathematics department, people still remember that like 4 years ago, they all worked on this kind of problem. But you people at MIT and co, I feel like you're like, I don't know, now you realize you don't care a bit, like, you know, you don't care so much about this anymore. So it's like, because like, you know, you were hearing yesterday, now like SGD is essentially online, and like on my first slide of notation, there's gonna be, we have a finite data set, you know? But I'll try to convince you that like, this stuff are still somewhat relevant. And worst case scenario, there is gonna be relevant when you have a small data set. So you can call me Pierre, feel free to interrupt at any time. I hope I'm gonna finish 5 minutes early, but we'll see. I'm gonna speak about like a paper I did like alone and a paper I did with Tommy and Andrea, which is a collaborator of us. And but like actually when I planned this talk, I thought it was a lecture, not a talk. So it's like it's gonna be like half lecture, half talk, okay? And so it's gonna start with like checking in on my audience, okay? So I assume you all kind of know what we're speaking about. That is like training neural networks, but like I want to know from you, or at least like before coming yesterday and seeing that everyone was assuming you all know everything, and you probably all know everything, I wanted to know, for example, like, who does not know what gradient descent is? Cool. Don't be shy. Yesterday I've been very shy when Aaron was speaking. I was like, who does not think, like, I was actually on the yes side. So I thought that like you can get there with scale. But then like everyone was saying no, and so I like didn't feel like saying it. But so good. You're braver than me for sure. Who did not take a course that dealt with optimization? Okay, cool. And like, who doesn't know that like, you know, you have like many optimization thing, but like when stuff are not convex, or when like your landscape you're going down is not nice, then like you may have problems with convergence. Cool, okay. And who does not know how to prove that like ReLU networks converge to a global minimum? Oh, fuck, I hoped you knew. You know, like this question is like, I hoped someone knew on the audience, but okay, too bad. Okay, cool, so like, I had some hopes for the audience, and I think you matched my hope. So like I hope the talk or the lecture it's good. So like let's start very briefly with gradient descent. What is gradient descent? So like essentially we have like a landscape, okay, and we want to find the minimum. We have a function. We want to find the minimum of the function. And like throughout the talk, you can think of, I don't know, you're on the mountains, you see a river down there, and it's like, what's an algorithm to get down to the river, okay? And gradient descent is like the most basic way to get down the river. So you have a function from RD to R, and it's like in the landscape metaphor, it's R2, okay? And R is the elevation. And you want to get to the lowest elevation. And you want to get there, and you want to get there fast enough, okay? So we want to find one of the minima. Maybe there's a river, and the river or a lake, and the lake is like, all the points on the lake are all at the same elevation. So it's like you want to get to the lake. Sometimes you don't really care where you get to the lake, but sometimes you care, and this is going to be the case later. And how can you do that? Like you can you're somewhere and say, oh, in what direction am I going down? And you do a step in that direction, you know? This is gradient descent. So it's like you take the gradient is like points towards going up. And so what you do is like, I'll do a step behind, okay? And this step is like, the size of the step is gonna be called step size or learning rate, okay? And it's gonna be my eta. And so again, like my position at time I plus 1 is gonna be my position at I minus a step in the direction in which it grows the most. So like plus a step in the direction in which I go the downest, let's say. And so like as an example, let's take the function that takes a vector. I'll call my vector theta, okay? So there is like theta 1, theta 2, theta 3, theta d in dimension d. And let's take the function that is like the first component square, okay? So like, you know what the minimum is, or like a minimum here is like every point there's like, I don't care about from the second to the d component, right? But I care that the first component is 0. This is the minimum. These are the minimum of this function, right? And so like, let's do gradient descent and let's see how gradient descent work here. And like, so we want to find the minimum. We start from theta 0 somewhere, wherever I am like during my hike, okay? And I say, oh, okay, I want to go down. So we said gradient descent is like, you take the place where you were, you compute the gradient, and you do one step back. And that's going to be the place where you're going to be, right? So it's like, okay, what's the gradient of this function in theta 1? Well, in theta 1, we have a quadratic, so we can compute this gradient. What's the gradient of this function in theta 2? Well, this function does not depend on theta 2, okay? And we'll call later during the talk, essentially theta 2 is not in the support of this function, okay? And so actually, the gradient in theta 2 of this function is 0, okay? And so like essentially gradient descent on this function is like keeping you where you are on the second, third diff component and going down on the first component. Does it make sense? So essentially, like when you take the derivative there and you do the step, you realize that like every component j is getting shrunk by 1 minus 2 step, and this like delta is like some mathematician kind of thing. It means like if j is 1, this is 1. If j is different than 1, this is 0, okay? So essentially, like on the first component, you're going down on, like you're shrinking of 1 minus 2 over eta, and all the other ones, you're multiplying by 1. It's the same, okay? And the minimum we find, I was saying, is like exactly where we started on some components, and then 0 on the first one. Is everyone clear with this thing? Do you have a grasp of what the gradient descent is now? Cool. And so in a sense, we characterize the speed of convergence because I told you it's shrinking by 1 minus 2 eta multiplying by that. And so now we have a speed. Like if you want to get to epsilon in the first component, you know that like you have the iterative formula to get like how many steps you need to get to epsilon. And we also found the location of convergence. And this location of convergence, what that is essentially the closest point to your initialization that was lying on the beach over the lake, right? So it's like, if you look at this is essentially the landscape, your landscape for this function, okay? And like, so on the first dimension, we're going down, And on all the other ones, we're like, it's like our landscape is flat, okay? Because like we're not getting anything by moving in that direction. And essentially what gradient descent is doing here is like going down and touching the river. Now it's a river because it's two-dimensional. Touching the river in the place that was like the closest to where we started, okay? Cool. This is not the case for neural networks. So first of all, we don't know if we converge. We don't know to what speed we converge, of course. But we also don't know to which minima we go. So it's like, to which minimum we go. We don't know where we touch in the river. And we'll see later that like, actually like if I massage a bit my gradient descent and like I take different versions of gradient descent, actually those different versions go in very different places along the river. And this is gonna be essentially the pitch of my talk, trying to come up with like how the different versions of gradient descent pick the place on the beach where they go to the lake, okay? So now the talk starts, and I'll give you some motivation, okay? Some motivation to study this problem. Like, you heard from many people now that like, you want to understand like why neural networks generalize, or how neural networks generalize, or when neural networks generalize. And generalize means that like, it works, like the neural network when you put it in production works essentially, okay? And people realize that like, for example, this is a matrix completion problem. It's not really relevant what problem this is. And this is like a graph that I copy-pasted from a talk of Nathan Zrebro, but I asked permission. And here they show that like on the same problem, when you use like different algorithms, so it's like you use either GD, or you use a regularized GD, or you rewrite the problem in some different way, then actually you consistently go to very different minima with very, very different algorithms, okay? And like from an optimization perspective, so like getting down to the river, it may think that like all the points on the river are the same kind of minimum, but in practice, this is not the case, okay? So it's like you have that like some minima generalize well and some minima generalize badly. So the question about generalization, like the way I see, then like I'm sure people disagree with me on this in this audience, but like the way I see generalization, at least when you have a finite data set and you have like a model in which I could check this kind of thing, was like about location of convergence. So I'm an applied math person, I do optimization. Like the only thing I look at is the optimization problem by AI. And essentially it's like, can we train? It means, do I converge? How fast? But like, does it generalize the minimum that I find? Is a question about location of convergence for me, okay? And how are the loss landscape of neural networks? Like, how are like the river made, you know? So it's like there are many different minima, and this has been known for long. And I was saying like different algorithms find different minima consistently. And so like, in a way, the way I see this problem and the way the community was seeing this problem in 2020, maybe not anymore, I was like, it's about how the algorithm travels those landscapes, okay? And so I'll show you an example real quick. And it's like, okay, let me take this like amazing data set that is like 5 data points in a W shape in 1 dimension. Let me initialize and take a certain learning rate and do gradient descent there. Well, very often, gradient descent really quickly finds a minimum. The problem is that like, this is a minimum, and this is actually a minimum that gradient descent finds. You know, this is like, this minimum here is perfectly balanced, like the distance from here to here and from here to here is exactly 1/2 of the distance from here to here. This is like a perfect minimum from the optimization landscape perspective. But actually, from a machine learning perspective, this is a badly generalizing minimum. Because when I start like sampling in real life data points, then I'll sample data points here, data points here, data points here, and actually the algorithm, like my AI, doesn't properly predict those minima, right? But like right there, I'm at this local minimum that GD found. Okay, let me start running stochastic gradient descent, whatever there is, okay? Then like what happens is that actually like stochastic gradient descent starts moving around, okay? Starts moving around, and at some point, like you see that this function that like oscillates, like, you know, like oscillates around this function, so you have like some perturbation of this first function. At some point you escape. And you escape real quick to this one, which is like kind of an amazing global minimum, okay? Some people may tell me, oh, but actually the data points on this line are not well fitted. Yes, but your training data is all fitted, and for sure this like works much better than this one here, okay? So the takeaways. Yes. Sorry, I didn't see questions. Please speak. I know it's usually not considered polite, but I don't care.
But you don't, like, if you just have the information of 5 data points, you don't know the underlying data. Like, you don't know it's a W that you're trying to fit.
Absolutely.
So then there's little difference between.
Absolutely, but still this one's wrong and this one's correct. Like, from your point of view, this one's wrong and this one's correct. Does it make sense? Yeah, of course, like I could have any data point in here and also any data point in here, but this one fit in the training set and this one not. So it's like before putting assumptions of this data set that actually comes, like essentially when I was telling to you a W, I was saying, oh, am I actually assuming that this is like the easiest possible data generating process that generates this W, okay? And this is what she's calling me out. Yes, I actually don't know what's going on here in the real distribution. Maybe there is a sinus and like the sine and goes like this, okay? But still, like here, my training data is fitted and here not, okay? So at least you can trust me on that. Yes? Cool. So the takeaways, like the first takeaways is like in general we have many minima, and which one you find actually matters, okay? Yes?
I mean, I guess related to the previous slide, like you differentiate between local minima and global minima, or like do you care about not finding a local minima but finding a global minima on the training set, or finding like the best global minima that will generalize better? Because this is not, like this is only local versus global minima.
Right. Later I'll care about, within the global minima, finding one that is like better represented in the parameter space. Now it was just a lecture-like example. Yeah, sorry. Like, is the person I'm fearing the most. Oops. Okay, cool. So there are many minima. Which one you find matters, and also like different algorithms find different minima. I showed you with like a very toy example, and we're interested in so in this talk I'll be interested in the implicit regularization of the optimizer. This meant in the literature many different things, but like the thing I'm meaning by that is like essentially, can we try to characterize what minima algorithm find? Well, actually we'll characterize, we won't characterize that, but like I'll tell you, when you're in these places, mini-batch SGD goes away. This is gonna be essentially what I'm gonna tell you in the first 2/3 of this like talk, okay? And so like, how is the landscape? Like, okay, wait. And so essentially we're not interested now in like how cheap and how quick is the convergence, but like in a chiefly non-convex way, like landscape. So it's like where you're like like you don't have like just like a valley that's going down, but like stuff are happening, like essentially where we're going. And again, I won't answer this question. I will just highlight a feature in the first part of mini batch SGD that like may actually lead us to answer this question. Cool. So like so the minima in the landscape of neural network, actually they lie on a high-dimensional manifold. What does this like mathematical jargon mean? It means that like there are like some rivers and lakes in which like all the points are minima. Okay? It's not there's like a minimum here and a minimum there, and so like it depends on like in which valley I get. Okay? It's like within every valley, so yes, from a certain point of view, but within every valley, there are like, I don't know. For example, in our previous case, there was like a d-1 dimensional manifold of minima. Okay, there was like, in that case, was a linear space, and it's like any of the second d-1 component could be any value, and that was still a minimum. Okay? And so essentially, the question is like, where the algorithm goes can be refined if we care about this setting, or at least if we care about the second part of the training where like we already picked our valley, to how do the algorithms pick a minimum once they're close to the coast? So it's like you're close to the coast, there are many places where you can put your umbrella, okay? And now you're trying to pick the best on the beach. Like you're looking around, there's like, where on the beach should I go? You know, like this is essentially what the question somehow boils down to once I message it this way. Cool. So it's like actually this question, like when you try to mathematize it, becomes, imagine I'm in a stationary manifold. So it's like everything's pretty flat around me. I'm I still can see a direction in which I go down, but like all my landscape around is like kind of flat the same. Like here, how do the different algorithms approach this problem of finding a minimum? Okay, and like empirically, they like we realize even in toy model they do it differently, and now we'll get through it. So, but like let's speak about the algorithm first. Okay, so like people work with mini batch SGD. What does this mean? So like, I have a set of parametric functions, okay, and those are like my loss on every data point. And the goal is finding the minimum of my average over the data points of the loss. So here, like theta are the parameters on which I'm optimizing. The z's are, okay, indices, but are actually my data points, okay? And like, my functions are like kind of smooth everywhere, okay, for what this means. And essentially what happens in real-world neural networks is that like my model, so like the number of theta's parameter that I have is too big. So usually I want a gradient-based methods for whoever understands this thing. Like I cannot do a second order method because like computing the Hessian is too much. And also like the loss is an average. I have many data points. So I'm like, you know what? Instead of like to compute the gradient of a sum of functions, like you have to compute the gradient of all those functions and then sum that up. Actually, I'm taking just 10 data points at a time. I compute the gradient there, I do a step. Then other 10 data points. Then other 10 data points, you know? So it's like, this is called mini batching, okay? So like we're not doing gradient descent, we're doing like the most computationally feasible, if you want, version of gradient descent. And so like to set notation again, like parameters at the I+1 step, it's parameters at the ith step minus my step size and the average 1 over b, when I take b data points in my batch I+1, the gradient on those data points in that batch. Questions? Cool. And now you may ask me, how do I sample those batches here? Okay, it's like, did anyone think about how to find the subset of the data set to look at each step? Well, there are like essentially two ways to do it, like two common ways to do it. There are more, but the important ones are two. And one is with replacement. This means that I'm sampling with replacement. As I take a ball out, I put it back in. So it's like I sample a data point, I sample a batch, and then I put all those data points back in when I have to sample the next batch. This is very nice mathematically because now every step is independent. Those batches are independent, those steps are independent. I can use like a lot of very nice mathematics that like people developed for us. But then there's another way, and it's like I sampled this batch, so I took out those like B data points, and those I don't put them in again. Like I sample a batch between the data points that are still in, okay? So that like I'm sure that I see all data points at some, by some time, okay? And then when I've saw them all, I put everything back in, and I restart with this thing, okay? And those two algorithms may seem very similar, but the mathematical nature of how they behave is gonna be different. And this is like essentially what the first part of the talk is gonna be about, okay? And cool, so like the thing is SGD is without replacement in practice when we have a fixed data set. And the reasons are multiple. So like first of all, it's because that's the standard of TensorFlow and PyTorch, and like most of you never touch those standards, okay? So but like why like, now you should ask me, why is that the standard, right? And like it's the standard for two different reasons. One, we had like some work of like 10 to 15 years ago that was telling us it generalizes better. And two, like we have some other work that tells us it's faster in any way. So faster computationally, because essentially a way you can do this without replacement is by reshuffling your data set and partitioning. You don't have to sample at every step. And sampling is like, I'm a numerical analysis person, and like when we study in school numerical analysis, like we know that like the products between matrices and sampling are those two things that we have to do it all the time, so they're actually computationally expensive, okay? But also it's faster from an optimization perspective. It converges faster. And, but so essentially we want to analyze this one, but now the steps are not independent, okay? So we cannot analyze, like use all these like magic tools that people produced for us. So about it's faster in every way, so Boutou found out in 2009 in a paper of 4 pages, that actually like the slope is twice the slope of SGD with replacement. And then there has been a lot of work towards proving this for like convex functions, so nice function in which we know we can go down. And in the end, I think the best result we have is by Mishenko et al. 2020. But now I care about this in practice generalizes better. And so this is a question, and it's also taking its time. Okay. And this one generalizes better, like essentially like to me, this is a question about location of convergence, I was saying. Okay? So it's like it means like it may go to different minima. Or like the mathematical nature of the effect that made it pick a minimum within the river may be different from the other one. Is that clear? Cool. Okay, and so actually like when we in this experiment here, like let's try to look at some graph to see what's going on here. Okay? So it's like when from this local minima of GD we run either SGD with and without replacement, actually like consistently different stuff happen. Like consistently the same thing happened, but in a different way. Okay? So essentially what happens is that like those algorithms start oscillating around. This is like my loss curve. So you say like at least the lower bound of it is like staying flat. and they oscillate a lot, and then at some point they escape down, and that is the global minima they found, okay? But like there are consistently in the hyperparameter different behaviors, and SGD with replacement oscillates a lot and escapes later. While SGD without replacement, then you know it, oscillates less and escapes faster, okay? And so essentially, like, I want to understand this phenomenon, like what's going on here. And so, yes?
This is the loss of the training.
Sorry?
This is the loss of the training.
The training loss, yes. And so let's take the easiest possible neural network that is the product between two numbers, okay? So it's like, I have one number, I'm multiplying by one other number, and this is gonna be my linear classifier. That is now is like, it's still linear in my data, but it's not linear anymore in my parameters, okay? And let's try to see on like why is this nice? Well, for no reason but there is like a two-dimensional landscape, and so I can plot it on my slide, okay? But like, let's see what's going on here. And what's going on here is that like, they actually travel those manifold of minima differently. So like, here is like, essentially like the manifold of minima is an hyperbole, like, you know, because theta 1 times theta 2 has to be 1. And so this can be 10 and 1/10 or 1 and 1, okay? And like, and essentially like when I do GD plus a Gaussian noise, or when I do SGD with replacement or SGD without replacement, like they all like somehow touch the manifold of minima in the same way, okay, when I initialize them close enough. But actually then, some of them, even without replacement, they start oscillating around very often, okay? And so like now like, I'm sure that Aaron gonna ask me, wait, there's no mini batch in this problem, right? Well, actually like I sampled some x's and some y's in a way that like when you write down the problem, it actually centers around here. So like now I have like some data points that align along the same function, linear function that is like y equal x, you know? And now I'm doing stochastic gradient descent on this problem. And actually what we see is that like SGD with replacement oscillates around the manifold of minima and moves towards this like amazing pink spot, which is our flattest solution or lowest norm solution, which is theta 1 equal theta 2 equal 1. And the same happens for without replacement, but without replacement moves faster and has less oscillations. And this is what we saw already in that like extremely toy ReLU example. Did I convince you guys? Okay. Go first.
It looks like the SGD without replacement, even though it has less oscillations, but it also looks like in the last part it travels a longer distance.
Sorry?
It looks like it covers a longer distance or longer time in the end.
Yeah, it shorts, you mean like it's getting closer and closer to the manifold? Yes. Yes.
What is the red one? It's another
The red is a different learning rate. So red is very small learning rate, yellow is very big learning rate. Yes?
With Gaussian noise must find the global minimum. It's like
all the points on this river are global minima. Because theta 1 times theta 2, the product of them, doesn't change.
So why did you decide that the pink one is the best?
The pink one is, I was saying, the best AKA, the lowest norm solution or the flattest solution. So when you compute the highest eigenvalue of the Hessian along the whole manifold, in the pink one is the lowest, and the pink place is the closest to the origin. The origin lies exactly here, okay? So it's like, I mean, it's not the best solution from generalization perspective in this problem, but it's like, has some like mathematical features of being good, you know? Yes?
Does it have anything to do with the initial condition?
No, actually. You see, I'm starting at 6, 1, and like whenever wherever I start, if the learning rate is small enough to actually converge, because otherwise it shoots me up, then as it reaches the manifold of minima, starts like going around. Cool, I think I'm like going kind of slow, but it's good. So what is going on here? Actually, like when you try to plot, and here is like gonna be the magical thing. So it's like essentially like when you find the minimum for a function, there is an average of stuff. We want to find the zero of the gradient. And so we want to find a place where the average gradient is zero. Let me now plot the trace of the covariances of the gradient. So essentially, it's some form of like second moment of that quantity that I'm zeroing out. Well, actually, and this is like, of course, the case for the linear network I showed you, but this plot is like in the ReLU case. Actually, like here, like this is like the training, the loss dynamic on the W data set for SGD without replacement. Actually, here, like, there are like the gradient, like this trace of the covariance of the gradient, like it's doing weird thing in the phases in which I'm converging, because there is like I care about getting to zero. But then in the phases in which like I'm kind of like around zero, then what's going on is that like those trace of the covariance is going down. Okay? Okay, so, and now we get back to the theorem. So it's like, no, get back. We get to a theorem. That is like by far not strong enough to explain this phenomenon, but like at least I think gives a flavor of what the phenomenon is. There's a pointwise bias. Okay, so the question is like, imagine I'm somewhere during my hike and I get hit by a mosquito, I want to go down, okay? And like, I decided like doing mini batch SGD, it was a very bad metaphor for doing mini batch SGD, but I decide between which mini batch, which version of GD to do, okay? So where can I expect to be after k steps? So I'm like, okay, I use algorithm number 2. What is gonna be the expectation over the way I sample the batches of my theta k given theta 0? So like where I am at the k step given where I am at the 0th step, okay? And so this is like, and actually like I lied also for a second reason in the metaphor, because like I'm doing this close by a manifold, a stationary area, okay? Because actually what I'm interested in, try to convince you about it, is like what I do during the, like in the stationary areas, okay? And what we'll find is that like SGD does stuff like, does like steps at random that are like at least centered around GD steps. But SGD without replacement actually does like an additional step in expectation toward some certain direction, okay? And so like, how can I like analyze mathematically that? Like, I added these slides for the people that were like craving about mathematics, but like there's not gonna be much mathematics, but anyways. So it's like, let me Taylor expand at initialization my k step, okay? And then I have like, that like, I'm doing k step of the gradient in the batch 1, batch 2, batch 3, batch I, batch k, okay? But actually, I'm expanding also those gradient step at initialization. So I have a first order part that has like those gradient step if I was at theta 0. And then I have like some additional terms that tell me how actually that gradient step changed. And like the first part of those additional steps is like essentially the Hessian in the batches before, that is like how much the landscape changed by going like the steps of the batches before, times like that gradient step in the batch afterward, okay? And now like, just like staring at these like horrible equations, we can see that like when I do SGD with replacement, then it's like all those gradients are like centered around the gradient descent step. but they're noisy, okay? Well, actually, when I'm doing SGD without replacement, now allow me to say k is the epoch, so it's the number of batches in a data set. Well, actually, this thing sums up to k gradient steps, because I have exactly once every data point. And this is exactly k steps of gradient descent. And so what I have is that this part is centered but noised for SGD with replacement, but this part is deterministic for SGD without replacement. And now let's look at the second part. Like, this is also noisy and centered around that same part of the Taylor expansion for gradient descent for SGD with replacement, but it's different for SGD without replacement. So here, what's the point of SGD without replacement? That, like, I know that the data point, if it's in the batch 1, it's not going to be in the batch 2. And this means that those batches are dependent statistically. And so, like, now I have, like, the expectation of a product of things, and this is not anymore the product of expectation, but it's like, okay, it's a part that is the product of expectation, and a part that is like that thing without the product of expectation, and that thing hopefully is small, because, like, they're dependent but not that dependent. But actually here, I get something different in expectation, okay? So it's like, essentially what I'm saying here is that, like, in SGD with replacement, I have, like, a noisy centered steps here. In SGD without replacement, this is deterministic when I'm close to a manifold of minima. And here, not only I have, like, the oscillation coming up from this part, but actually I have also, like, a bias. So in expectation, I'm moving due to that part. Is this clear? Yes?
Could you say a little bit more on the noise-centered STG with replacement? Like, what?
Yeah, it's centered in the sense that, like, all those random variables are independent on each other, and their expectation is I'm subsampling from the gradient, the full batch gradient. Their expectation, if I'm subsampling uniformly, their expectation is exactly the full batch gradient. So they're centered around the full batch gradient, they're independent, and there's some noise given by my subsampling. Cool? Okay, and so, like, what we found, like, okay, let me skip on, like, analyzing this bias. But essentially, when I analyze this bias, like, I have an Hessian times a gradient. And this is, let me tell you, the derivative of the norm of the gradient squared. And so essentially I'm getting that, like, there is, like, the GD part, and then another part that is essentially the trace of the covariance of the gradients. And so essentially the behavior I'm saying is, like, wait, in expectation SGD is different. Because, like, I'm doing a GD steps, and then I'm, like, adding up a small step in another direction. But I'm doing it in expectation. And, like, essentially what I want to convey as a message is that, like, SGD with replacement very often goes in the same place where SGD without replacement goes. Bad news. But at least bad news for me. But because my paper is less relevant. But it goes there, SGD with replacement goes there, like, by, you oscillate a lot, and you end up in the place that is the widest, because, like, when you get there, then you oscillate less. Okay? Like, mathematicians would kill me for this kind of reasoning, but, like, this is essentially what it boils down to. But, like, SGD without replacement, it's oscillating less, because it comes from the second order, the oscillation. And there you have, like, a learning rate squared, and that learning rate may be small. So it's oscillating less. So it has that effect, but less, but also it has a bias. Okay? So I'm moving where the GD goes, and then to a second order in another direction. And actually, that direction, magical enough, like, aligns along the flat directions. So, like, you compute the math, I tried to compute that math for 2 years, and then at some point I realized that I told you a trace of the covariance. Actually, that's a weighted trace of the covariance, and those weights are along the eigenvalue, eigenvectors of the small eigenvalues. And so essentially what's going on is that like the GD part is taking me down, but this other thing is moving me across. And so in expectation, I'm doing a small step at every epoch, okay? So maybe that's not relevant for online SGD. For online SGD, I believe it's relevant with replacement kind of thing. But I'm moving in this direction, okay? And what does it mean I'm moving in this direction? It means that like I'm doing a step there until I'm at the minimum of my trace of the covariance within this manifold of minimum. Because if I move away, then the GD part is much bigger and drags me down again, okay? So essentially what I'm saying is this thing. So on the sharp direction, I follow SGD with replacement or GD in expectation. On the flat directions, I have this regularizer. And then like, actually I think I'm not saying for time is that like, if like the directions are too sharp, actually this like regularizer shoots you away. And this like, I was very excited, I thought could be an explanation for why SGD doesn't train at the edge of stability. Sadly, I actually don't think that's the explanation. But yes. And again, I was saying it's a weighted trace of the covariance. So this S is essentially diagonal matrix. So it's like I'm taking the trace, so the sum of the eigenvalues, and I'm putting some weights in front of the eigenvalues. Yes?
Do you have a sense of like what is the magnitude of the trace of the covariance compared to the gradient?
Yeah, let's do it offline. But essentially, like the multiplier around this thing. So, okay, essentially for problems that are linear in the parameters, this trace of the covariance is the same everywhere. So in linear regression, you don't see this effect. But when it starts being like, I don't know, the way I see it from a very bad optimization perspective is like when the manifold tilts, then this starts happening and moves in the direction in which the manifold opens up. And like to come back to the size of this thing, well, it depends on the size of the opening up, of course, but also essentially here I have like eta squared, but also like that sum is like of like k squared half terms, because I had like every Hessian, like Hessian and gradients, and like every Hessian before. So essentially I have like a divided by data set size, because this was coming up of the expectation, and then you multiply by the number of steps squared, and one of them kills it with the divided by data set size, and then like the other one that would be too big, anyways, in practical gets killed by learning rate squared, but still you have like a O of 1 kind of step in general. Did I answer your question? And so, and also like I'm very proud to say that like this analysis is very general. So it's like people to try to get results like that, where do I go to the river? Usually you used to put like more assumptions like on the model, on the injecting noise. And here like I have no assumptions like that. And I'm not limited to toy models. I have like every function that is like smooth enough. And also, previous analyses were saying, oh, I'm analyzing k steps at time, so I have like eta k to be very small, and eta k times the Hessian to be very small. And I kind of deleted this assumption from the thing. So I have, so like the implication number one is that actually this is the reason why I'm traveling the manifold and I'm doing it faster and with less oscillation. And I hope I convinced you about it. And like, also like an implication that I like always to say is like, well, escaping saddles. So like people know there are like a lot of saddles of every degree in the landscape of neural networks, and people worked a lot to prove that SGD with replacement is escaping those saddles. And there are some like super technical results, or at least super technical to me, that like they say if lambda is like the smallest eigenvalue, the speed SGD with replacement escapes it is like lambda to the minus 3.5. And here I'm saying, listen, like I see the GD part doesn't move, but like my bias, my small bias actually keeps moving in most of those saddles. And so under similar assumptions to the ones, aka there are escaping directions, in which I can say that like SGD with replacement escapes in this with this speed. Actually, I can say it escapes with this speed because simply the regularizer step doesn't stop moving. Okay? And so the picture is like, while with SGD with replacement is like, I shoot around, at some point I'm far enough from the saddle that the GD part kicks me out. Here the picture is like, I keep moving because of my regularizer, and then at some point the GD will kick me down. Yes?
Is this for functions with strict saddles? So you
This is for strict saddles. I also analyze the non-strict saddles. But like this like speed is for strict saddles. But for sorry?
What is lambda? Is it the smallest?
The smallest eigenvalue of the Hessian.
In terms of magnitude or?
In terms of like the biggest of the negative ones. Yeah, the biggest in magnitude of the negative ones. And so also like as I hopefully convinced you, there is a strong, like maybe they go to the same minima, but from a mathematical perspective, SGD with and without replacement, and I put the online in the with, they actually act differently. And SGD with, like, it moves around the manifold of loss equals 0, while, like, by oscillating. Like, it's a completely stochastic kind of thing. But SGD without, it, like, jumps around, but the regularizer points you in one direction. And the GD, it just touches it and stops there. Cool, so, like, essentially, we understood what was going on here, I believe. Or, like, this is, like, kind of good enough for me. Yes?
How does this depend on the size of the data set?
The step. Yes, so this question is a good question in the sense that, like, the way that step depends on the size of the data set is the way I told you. But actually, if the data set is bigger, this is essentially one step of regularization at every epoch. So you're not, like, if this data set is too big, essentially you have to compute one step and you're moving on that step, but that's it, you know, because you see only one epoch. So it's like I can also tell you, like, maybe we converge if I allow to have infinite epochs, and I can prove some stuff like that. But actually, like, if you tell me, oh, my data set is 1 billion, and, like, I see it once or at most twice, then, like, you know, so yeah. And, but now, I want to get practical, because I was, like, assuming, like, not to have convinced you with this kind of thing, because you know that there are infinite data and you don't care anymore about the first assumption on my first slide. There was like, we have a data set of size n. And so like I want to show you that actually you can prove interesting stuff with it. And this is a joint work with Tommy and with Andrea, which was a student that was at Tommy's lab for the past 6 months. And the problem is the following. Okay, I have like you know, like vision data sets are usually very huge in dimensionality, and also language data are very huge in dimensionality because essentially there is like a dimension for every token, okay, or a dimension for every pixel, or 3 dimensions for every pixel. But actually, like, are all those pixels relevant? And it's like when we look at MNIST, it's easy to notice that like those pixels in the corner are not relevant, okay? So it's like probably like a good generalizing model will not depend on those pixels on the corner, okay? And like when I look at this more difficult data set, like, is this still the case? Well, actually it is. It's not any more pixels, but it's like there are some linear combinations of pixels that like don't tell us anything about the class in which we are. So for example, if you take, I don't know, the upper corner minus the upper left minus the upper right plus the down right minus the down left, this has like 0 to no information about the class you're in, okay? And so like we can see this like essentially like this doesn't tell us that like there's a linear combination of them that doesn't matter, but this like tell us it's like there is like a non-linear combination of that doesn't matter. But when you train a ResNet on Cypher 10, and then you look at like, what's the shape of the input of the head MLP. So it's like you're doing many convolutions, many residual things. And then at the end, you're doing linear regression on top of that. And what's the shape of like the stuff you get in this final input, in this final linear regression? Actually, you see that the spectrum, like, well, and then like you fit this linear regression onto your problem or classify, and then you see there are like essentially like just a few directions that like matter, and most of them do not. Okay, and so it's like, okay, maybe like you can argue that like in general like my target function depends on like many directions, but I'm doing a theory of MLP, and like those blocks within the model sometimes do not. And so the question is like, how do we treat mathematically? How do I understand what's going on? Well, we can say, oh, the support is like the lowest dimensional manifold that, like, on which I can find a model that like generalizes 95% of the time. And you can say, identify the support. I say the model identifies the support if when I move in the direction that are orthogonal to this manifold, then like my output of the model doesn't change. And then tell you more, I can say the first layer identifies the support if when I take 2 points in this manifold in this manifold that is like, I don't know, 9-dimensional, and then I add like 5 in an orthogonal direction to this manifold, and 5 in another orthogonal direction to the other data point, actually the first layer considers those 2 data points the same, okay? So it's like, now we're trying to understand, actually like, our data sometimes is like very high dimensional, but our target function depends on like just a few dimensions. And how do neural networks find those few dimensions? And like empirically, Andrea found that like, actually in most of the cases, the first layer is lower dimensional, and lower dimensional in a way that like puts all the weights on like along this like, for example, linear space. Okay, and this is like, for example, like when you train NIST with that I know is like very toy, but when you train NIST with an MLP, what you find actually is that like at initialization, this is the distribution of the singular values of your first layer. Well, if you train it with SGD with big batch, then you have like at convergence you have a certain distribution. But if you train it with SGD with very small mini batch, you have a very different distribution. And you know already where I want to go. I want to go that maybe the size of the batch and the size of the step size actually bias your, like, the way in which neural network find the support of the function. And the way Tomer would phrase this thing is a bigger batch size or a bigger, smaller batch size or a bigger learning rate actually biases towards low rank in the first layer. And so essentially, like, we run some experiments. This is still like the empirical part. And it's like, unlike models that like we know that are low dimensional because like we crafted them this way, we actually noticed that like, okay, this is like, I'm plotting the matrix of the first weights, the weights of the first layer. And initialization is like this. Well, at GD, I'm finding like a model that fits the data exactly as good as like GD with weight decay, actually better, or exactly as good as SGD, but it's like very close to the initialization one. And then as I drop the batch, like the second part, that is like the one that interacts with the feature of the input that are not relevant, actually goes down and down and down. And then when I do weight decay, of course, they converge to 0. Okay, and actually, like, my mental picture for this is like, you remember those landscape with that manifold, and GD that was going down and stopping there, and SGD that was going down and then starting moving along? Well, this is essentially what it happens here. Or at least, this is what I can prove that happens when you do linear networks, because I'm not that good, I cannot prove it for many models. But essentially, like, but all these algorithms, they touch the manifold in a point that is like the closest to initialization. And then by moving around along the manifold of minima, what am I doing? I'm actually regularizing this way. Like the effect of that, like moving around that manifold of minimum toward a place, on the first layer, in linear networks, and also in real, empirically, like on every network, like I can prove it on linear network, actually has this effect, like zeroing out the stuff that we don't care about. And so essentially, like I'm saying, smaller batch does it better. And we can see it like in practice, like now I'm training a ReLU MLP on NIST, and it's like, we spoke about the fact that those like inputs here are not relevant. Well, like when I train with a big batch SGD, this is like the size of the way they interact with that pixel there, okay? Actually, like my model is still interacting, or at least the first layer is still interacting. Then the model, like by switching off many ReLUs, is still cutting out the information that comes from here most of the time. But the model is still interacting with those pixels. And as I go down the batch, actually stops interacting with them. Yes?
There must be an optimal batch size, because I guess if you take the batch size to 1, you will start having...
If you take the batch size to 1, you don't converge anymore. If you converge, you do better. You do to a better minima, but you don't converge. Does it make sense?
Yeah, but which batch size is like...
Depends on the problem. Depends on like how hard is your landscape to go down, essentially. So, and we can see it here. It's like when you train, now I'm looking at the size of those weights that interact with those pixels we don't care about. Okay, I'm looking exactly at that. And it's like I'm training with GD and SGD and anything, like the trajectory is kind of the same until some point in which they diverge. And those pixels like go a bit down, but then they stabilize for GD. And they go down there much faster for like either smaller batch or for the same batch size for bigger learning rate. And then there's way decay that does better than everyone, but this is like another story. Like, you know, it's like we're playing basketball, and then like LeBron comes to the game. And yes, and actually like, so like what we can see from this picture and like from my theorems on linear networks is that like weight decay is the best. GD does it a bit, like gets down those weights, but at some point stops, and stops always too early, or at least very often when you take the probability on the initialization, stops too early. And the speed of shrinking depends on learning rate and batch size, and there are 2 phases for SGD. And what are the 2 phases? I'm going down to the manifold, and I'm oscillating and moving around, like parallelly to the manifold. And now for the last 5 minutes, like, this is not going to be a talk of zoology, but I feel like there is a big elephant in the room, and this is my elephant in the room. And I feel like the big elephant in the room is that, like, yesterday during the panel, I got stabbed multiple times. And I got stabbed by Aaron and by Jacob, that I don't know if it's here where. Okay, the strongest of the stabbings were like, we should move forward from gradient-based methods. And it's like, when that sentence arrived, like me and Tomer kind of like melted on the thing. But actually, I agree. It's just that I worked on that for 4 years. So it's like now I'm like, and what next? You know, it's like I'll do my startup. But like, and not like maybe a stabbing that we can try to address, and fun fact, I will not really, is like, oh, now like we should move forward from implicit regularization. They didn't say exactly this, but like we should move, like all those theories for GD or SGD, we should move forward from that. And it's like blah, 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 okay? And so like now I was planning to trying to convince people by working some math on the iPad that like actually maybe doing this implicit regularization thing is still relevant. And this is the part that I added yesterday from 1 a.m. to 3 a.m. Because of like how the panel went. And this is also the reason why I switched from Camel to Marlboro. This is usually a very bad sign. And essentially, I want you to think. So let's take this model again. And like I'm not sure even I agree on the argument I'm trying to make for the. I think I'll go 2 minutes over time. The argument I'll try to make, but like, I hope there's food for thought, and like, we may discuss it, and then write the paper. We still care about implicit regularization, or like we don't care anymore about implicit regularization. Okay, it's like when you do SGD, online SGD, and like, in this model that is one-dimensional, this may be the reason why this is still the case. Maybe that like everything breaks when it's multi-dimensional. Some question? No. No questions? Okay. Well, here, if I sample new x's and new y's, but that aligns around 1, 1, then I still have on expectation this manifold. And still, also on the loss in expectation, all those points here are minima. And what is like online SGD doing is essentially sampling IID. So it's like from a mathematical perspective, the nature of this effect is exactly the one of SGD with replacement. So maybe those things that I'm saying, and like the thing that I'll prove in 2 minutes about the support, still matters now that like we're doing online, we have infinite data, etc., etc., etc. Then like, when we move on from gradient-based methods, well, I'll try to sell myself to mathematics department, trying to convince them that I did some relevant mathematics instead of like some relevant machine learning theory. But like, but still like, maybe that like, still like those stuff matter for online SGD. And I'll, yes?
So the first one, in the previous, the first one, each point here is one epoch, or is just, for example, for SGD is a batch?
It is one epoch, I believe.
And the second question is, we're training everything with the same learning rate.
Yes, I'm keeping the learning rate constant. Yes. And so, like, let me restart with, I have a data set, but now I'm not saying the size of the data set, okay? I removed this N yesterday at 2:46 a.m. And let me say, oh, I have like this following linear model in the input, but non-linear in the parameters. And I want to see, I do one step of GD. What is one step of GD? Well, I think either I differentiate this thing, and like I get like this 2 goes away, a 2 appears there, of course I forgot about it. And then I have like, I'm doing the derivative in like theta I, so I get like essentially all of them but theta I that get multiplied, okay? And so now I'm saying, wait, I'm speaking of irrelevant components. So what I want to prove is that like the weight that interact with the components that goes like that are not relevant for the target function go to 0. So I'm saying, oh, okay, actually consider my y to be 0, okay? Or like the conditional expectation that of my y given x along this direction being 0. This is then the way you frame it for like multidimensional linear networks. And now I can write this thing but instead of y, I put 0, and I forgot an x here. Otherwise, there should be an x squared that multiplies. But essentially, now I can rewrite this. Okay, this is the product of all the thetas except the ith layer. So this is the product of like the stuff, like all the other layers, but the one in which I'm looking at, because every parameter is a layer now. And here, well, here I have the layer I'm looking at times all the other ones. And so I can say, hey, wait a second. This gradient descent step, it's actually doing multiplying 1 minus eta, the product of all the other layers squared. This gets very ugly, like when like depth is not, width is not 1. But anyways, this is like the point. Times theta 1 I. And so I'm actually, like GD is shrinking, like the parts of the layers that interact with like with the relevant components. And if you look at this quantity, now let's say, okay, but I randomly initialize those theta. And theta 3 is the smallest of all of them. But so when you see theta 3 is the smallest of all of them, it means that like the product of the j different than 3 of theta j squared is the biggest of the product of this kind. And theta j is the smallest of the product of this kind. And what does this mean? It means that like the one that is the smallest at initialization, the layer that is the smallest at initialization, actually converges to 0 faster than the others. And what does this mean? This means that GD identifies the support in any of the layers. I can do this thing for ReLU too. And like for ReLU, what happens is that like if there's a switch of sign, at some point it's the ReLU to identify the support by switching off. It's not even like an intermediate layer. But, and this is like, but like when I do SGD, and I have like some assumption on the data or like whatever that like tells me that I'm oscillating, those are called edge of stability. Those are called like the linear model is misspecified. Those are called we have catapult effect, aka the mini batch matrix expectation of XX transpose is big. Okay. Then like what happening is like I'm oscillating. Yes. Yes. It's the last slide. And like what's going on in this case. For SGD is that like now you have to imagine this line, blue line, to be the axis. Okay, so it's like instead of having like 10, 1/10, I have like 10, 0, 0, 0, 0, 10. Okay, and so what happens also here is that like, well, I send to 0 the one that initializes at the smallest between the layers. But then oscillating, I move towards the origin. And so, like, after a long time, unfortunately a long time, I send to 0 also the second smallest. And after an even longer time, I send to 0 also the third smallest, etc., 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 until like all of the layers are sent to 0. So it's like if I have an assumption that tells me the SGD dynamics oscillates, then like SGD is like strongly regularizing in infinite time. Because it's sending like all of them to 0, not just like the one that was initialized smallest. End of the story.